Hi, I want to start today with talking about session 1 of operations management, and we're going to deal with process mapping and bottlenecks. Here are some objectives for today. So why do you care about using process maps? Well, what it does is it quickly provides a visual representation of a process so that anybody coming up and looking at a process does not necessarily need to walk it themselves, but they can view it quickly on a sheet of paper. So where is process mapping used and why is it used? So again, it's a graphical depiction of all the steps in a process. It's used to help optimize a process, and we'll talk about that later in examining the most the lengthiest step in the process, such as the bottleneck. It's used in Six Sigma, Lean Six Sigma, Lean, root cause analysis, and so on. So it's heavily used in a lot of different performance improvement type of analyses. So here's some common symbols for the process map. You have this triangle, which is an inventory or weighting, something again you do not want to have. So that should trigger that is a bad thing that's happening in your process. Oval is just kind of the start or stop of your process. The big block arrows typically used to show transportation. Again, these are not that arrow is not used in all processes. The rectangle is always used, and that is to show a specific task. So it could be in a hospital visit. It could be the first step is the patient check-in. Okay, so check-in becomes your rectangle. A diamond is a decision point. So you could have a yes or no that veers off from this decision point. So one decision point could essentially be patient brought medication list, and then the answer is yes or no. And so then if it's yes, you take one course of action and follow it one path, and if it's no, then you'd follow an alternate path. And then again, this kind of half oval is to show a delay in a process. So you have this half oval, you have the triangle. Those are typically negative things in a process map. Shows some delay or waiting. So here in another process map example, we'll talk about the ED. So let's start here where the patient arrives at the ED, and then they move on to the clinical triage step. So again, we talked about process steps being a rectangle, and so there's some triage that goes on there. And then you move off to the right where you have here complexity. So this is a decision point. Is the complexity high or is it low? If it's high, then they'll go up to the intensive ED care. And if it's in the low complexity, then they'll have to wait. Again, we talked about this being the shape of a weighting, like a half oval. And then they get triage for financial reasons. Okay, so you can kind of see how these different shapes represent different process steps, whether it's a decision point, such as in the this shape right here with the complexity, or if it is an actual process step like the rectangle, or some sort of weighting mechanism, and that with the half oval. Okay, and ultimately you get down to the end, and we talked about the beginning and end being a circle. So one thing I'd like to note with this is it's great, it's a great process map, indicates what's going on, but it would be even better if there were some times involved here. So you put some times under how long does somebody have to wait? Is it on average 5 minutes? What is it? How long does it take to triage at the clinical step? So if you have that in there, you can get a better visual representation of the process and where maybe there are problems. So here's some process terms. I'm not going to spend a whole lot of time on it. You can read these on your own. So let's go into the next step, which is next slide, process metrics. So the capacity of the process is the maximum possible output that a process can produce. So if it takes me 1 hour to do a process step, and I have 8 hours in a day, the maximum capacity is 8 units, or 8 patients, whatever it is, whatever your unit happens to be. Throughput time is going to be the overall time in the process. So it includes everything: wait times, process times for different steps, transports. It's really all of that. And so the longest step in the path really has a direct bearing on your throughput time, because if you can reduce that, you can reduce the overall process and increase your overall throughput, I should say. The process time, the difference between process and cycle time considers the number of full-time equivalents, or FTEs. And so a person, 2 part-time workers working half-time comprise 1 FTE. And so again, the process time does not factor in any FTEs, whereas the cycle time does. And the formulas are right there. So I mentioned the bottleneck. The bottleneck is critical to the process. It really dictates how many units you can get through, and it's the process with the longest cycle time on the critical path. So the critical path is your longest path in a process. There might be simultaneous things that are going on. Maybe there's two processes that are going on at the same time. So it's whatever process has the longest, or the longest route. And a bottleneck, the reason again it's so important is because if you can reduce that time, you can ultimately get people through your process faster. Take for example a patient, and the patient has 10 steps. One step takes 15 minutes and all the others are 10. And I have a unique staff member at each step in the process. Well, if I have 10 minutes at step 1, 10 minutes at step 2, my patient continues to flow through that system, but then if it takes 15 at step 5, there ultimately becomes this backlog at step 5, because it takes 15, whereas all the other steps were 10. Value added time and non-value added time, the difference here is that value added, you need to think of it in terms of the customer. So is the customer getting some benefit from what you're doing? And the non-value added is just the opposite. Again, you want to think of this in terms of the customer. So we'll talk about some more of these in the ensuing slides. Again, process metrics, another one is takt time. Takt time, the formula is right there, and it considers the available work time divided by the demand. And workers required, you can see the formula there, and the utilization, which is the proportion of the capacities that's actually being used. So we talked about what the capacity is, what the formula, how you calculate that. The utilization is just the proportion of that that's being used by the process. And so you can calculate the utilization for each individual process step. So let's roll through an example. Here you have 5 different steps, and it's listed in the top bullet how many seconds it takes for each one of the steps. So given that the shop is open from 8 to 5, so that's a 9-hour period with a 1-hour shutdown for lunch. So each step must be finished before the next step can start. That's one assumption we're going to make here, and the demand is 600 mirrors per day. Okay, so to calculate the takt time, how did we say we would calculate that? Well, we take the available time and divide it by the demand on a given day. So if our available time in a given day is 8 hours, because our shop, while the shop is open for 9, we're only actually operating for 8. So you only consider the 8 hours as available time. And so 8 hours times 60 minutes, it gives you 480 minutes. And then if demand is 600, you divide it and you find out that you have, what this tells you is you have to get through a mirror every 48 seconds. So a mirror needs to come off that floor every 48 seconds in order for you to meet demand. And we already showed you the workers required, but in this case, you'd roughly need 3 workers to do this task. So Little's law, the formula again is people or things in the system, so how many, the number, divided by the arrival rate. So in this example, we have 200 patients in an 8-hour day, so you could say the arrival rate is 25 per hour. And then the average number in the system, which includes your waiting room, your exam rooms, etc., is 15. So again, you use the equation from up top, and it becomes a very simple equation or simple calculation. So 0.6 hours is the average that every patient is spending in your clinic. So that's what the average throughput time tells you. So now here I want to show you another example of, or the first example of a process map. So we showed you one earlier with the ED. This one's going to show you it a little bit differently and now show some wait times, and they have the wait times with this triangle. So we said inventory or wait times could use a triangle. You could also use that half oval shape that we talked about before. So here the first step is you check in, which takes 3 minutes. Then you wait for 15 minutes. You move to the examining room, which takes 2 more minutes. We said movement, you can use those triangles. Then the nurse does the prelim exam for 5 minutes. You wait again, and so on and so forth until the visit is complete. So here if we want to look at patient check-in cycle time, we say that's 3 minutes. So let's go back to the previous slide, and we can see that right here, patient check-in time is 3 minutes. Okay? So now the bottleneck, cycle time for the longest task. So let's look at the tasks. So we said the tasks are these process steps that are shaped like a rectangle. So you see this one's 3 minutes, you go down here, this one's 5, this one's 20. Okay, so you pick the longest one, which is the 20 minutes, the physician exam and consultation. So now we've determined the bottleneck. So what is the overall throughput time? How long does it take one person to get through the system? So let's look at this back at the process. We said throughput considers everything, considers the wait times as well as the actual process times. So basically all you're doing is you're taking each individual step. You start with a patient check-in, that's 3, then you wait for 15, then you move for 2, and so on, and so you add up all the times. So your throughput time is 70 minutes. So let's answer this last question. If the clinic is open and functional for 8 hours, how many patients can it serve in one day? Okay, so in order to answer this question, what you have to do is you have to consider the bottleneck. It's not necessarily the throughput time because some of these steps are being performed simultaneously. So what you want to do is you want to look at the overall longest step, which is the physician exam, that's 20 minutes long. And you just divide your available time for that day by the 20 minutes. So if I have 8 hours, that means I have 480 minutes in a day, and each exam takes 20. So I divide the 480 by 20. And that gives me the 24 patients is what we can theoretically see in one day. Again, remember the bottleneck is the process step with the longest cycle time. So we care because it slows down the whole process. You reduce that bottleneck time, you reduce the overall the time the patient spends in the system, and you can get more people through the system. So let's go back to this example. If let's say that was 10 minutes for this physician exam and consultation instead of 20, I want to look back again at the process. Is it still the bottleneck? Yes, it still would be the bottleneck. It's still the longest time. So now again, if it's 10 minutes to get, 10 minutes to get through the physician exam and consultation, now I could theoretically serve how many people? Well, 48. Okay, so I just reduced the time in that one step, and now I've doubled the amount of people I can serve in one day. Okay, so I didn't adjust any other task, just that one, and now I've doubled my time. If I go back and look at this process again, and let's say I reduce the patient check-in time to maybe 2 minutes. That is not going to have any effect on the amount of, or the number of patients you are going to see in one day. Again, because it is not the bottleneck step. Okay, here's another example of the bottleneck, or of a process, and let's look at what is the bottleneck here. So now I have all these different steps, and you see there's, in one case, there's 2 steps going on at the same time. So maybe there's 2 different people that are managing this part of the process. So you have a check for the credit rating, and then you can also have a loan application going into the system. Okay, so both of those are going on after you categorize the loans. Okay, so the bottleneck step, again, is the step with the longest time. So if I look at this, I see categorize loans, 20 minutes. So that's the longest step. So that's your bottleneck. Now, if I want to look at the throughput time, okay, so what do I do when I calculate the throughput time? You take the sum of all the process steps, all the waiting. So here, if I want to do that, I take this 15 minutes, I add in 20 minutes, and now instead of taking both of these, again, because both are going in at the same time, I just take the longer of the 2. So I take this check for credit rating, and then I add in this here. So what is your throughput time? Well, in this example, your throughput time is 60 minutes, because you'd have the 15 here plus the 20 plus 15 plus 10. So what is the maximum number of loans that can be processed in 5 hours? So if you think back to that previous example, we took the available time, and then we divided it by the amount of time for that bottleneck step. Okay, so 5 hours, that you would think you'd have 300 minutes. So 300 minutes divided by the 20 minutes for that step, and that means you could have 15 people come through in 5 hours, or 15 loans. Okay, so let's go through another bottleneck example, and here it's very similar to the last one. So here's a process for cleaning teeth. You can kind of quickly see, again, and this is the value of having a process map, you can see what takes the longest period of time, and that's the cleaning step. So the cleaning is going to be the bottleneck. See, 24 minutes for every unit. Okay. So here we're again going to look at this. All possible paths must be compared. So when you try to identify the throughput, what you need to do is consider how long does it take each path, and you come up with the total time for each path, and then it's whatever is the longest path. So that is your throughput. So here we have an exam path. The exam path takes 27 minutes, and then we have a cleaning path which takes 46 minutes. So your throughput time, meaning the amount of time that it should take for one patient to get through the entire system, is 46 minutes. And the hourly capacity I didn't talk about earlier, the hourly capacity is 2.5 patients for this process, because you have 60 minutes in an hour, and again you take your bottleneck step, which is the cleaning at 24 minutes per unit. Okay, now we're going to talk about bottleneck example number 3. It's going to be similar to some of the other examples we talked about. We're going to go through A, B, and C on this example. We won't cover D. In order to cover D, you need some more information, such as the actual demand, and so we don't know the demand here. Okay, so in part A, let's say in a 4-hour morning, how many patients can be served in this system? So what we have to think about is what is the bottleneck step? So if we look at the table at the top, we can see the one with the lowest number here, here's our process time, and then we also know the number of workers, so we can basically do the cycle time as well. So in the receptionist, they can see 12 per hour. We look down at the list, we see the hygienist is 3 patients per hour. So that's clearly the lowest number per hour, meaning it takes 20 minutes to see, for the hygienist to see each of those patients. So even though we have 2 workers, that essentially means then we can now see 6 patients per hour. So that's still the lowest number in terms of cycle time. Or I should say the lowest number of patients per hour. And it takes the longest amount of time for that step per patient. Okay, so if we look at that part A again, now we're able to see 6 patients per hour. So in a 4-hour morning, how many patients can be served? So 6 per hour times 4 hours is 24 patients. So that's part A. Again, you will want to look at that bottleneck step. In part B, that is also answered by doing part A. So the bottleneck is the hygienist. Even though there are 2, it's still 6 patients per hour, which is less than the dentist. Okay, so then part C, assume that this system will always have 1 dentist. Okay, so the dentist, we saw they see 7 patients per hour. Okay, will adding staff in any other stage of the process improve capacity or throughput for the entire system? So again, we look at the dentist, they see 7 per hour, but the hygienist, again, is now only 6 per hour because we have 2 hygienists. Okay, so if we add staff to the hygienist, then we're ultimately able, let's say we add 1 more hygienist, now we'd be able to see 9 patients per hour for the hygienist step, which is better, or allows us to see more patients than the dentist step. So now we've shifted the bottleneck if we do this, and the dentist becomes the bottleneck. Okay, so we are able to see more patients, and so we would want to add staff to the hygienist, add another hygienist if it's a cost-effective solution. So again, there's no question that we'd reduce the amount of time a patient would spend in the system. We'd increase the number of patients that would go through the system. We would just have to evaluate if it's a cost-effective solution. Okay, so now to get into value stream mapping. It's a little bit different than what we've talked about earlier. Up to this point, we've talked about process mapping, bottlenecks, and so on. Those are ultimately going to be examined here in value stream mapping as well, but value stream mapping looks at things a little bit differently. So the difference with value stream maps is they look at whether a specific task is adding value or not adding value. And again, we said earlier, it's from the perspective of the patient. So is the patient, or the customer, I should say, getting any value from what you're doing? So here, in a hospital setting or healthcare setting, it's does the patient care about the activity? Does the activity transform the end product, meaning in terms of their overall visit in some way? So some non-value added steps, there's 2 types. There's the necessary or required non-value added step, and then there's the absolutely unnecessary step. So a lot of times the necessary deals with some regulations. We'll get into that in another slide or 2. So here again, non-value added steps, we said they add no value to the customer. So you need to think in terms of the customer, not in terms of what you as an organization thinks adds value. It's what is the customer getting anything from what you're doing? So the goal is ultimately to eliminate those non-value added steps, particularly those that are not necessary. So some non-value added types include transportation or motion activities, so where you're walking around unnecessarily. Inventory, non-value added. Waiting times. Of course, the customer doesn't want to wait. And then if you overproduce or overprocess, those are, again, something that is of no value to the customer. And then if you have defects, meaning maybe they had some negative outcome from their visit, a readmission. Or if you're talking about purchasing products in manufacturing, they get a defective product and they need to go and return it to the store. So in value stream mapping, again, here's a little bit more of a detailed breakdown of customer value added activities, non-value added, and then but required, and then non-value added, not required. Okay, so again, we talked about value added being something the customer would want. So if you're doing some sort of facility support, that's essential to the patient care. We need lights in order to take care of the patients. Maybe in surgery, it's the actual surgery itself. It could be the vitals taken before the surgery. It could be setting up the cart that's required to perform the surgery and get the necessary surgical supplies and equipment on that cart. So again, the customer receives some value from those type of things. Now we could look at non-value added but required, and a lot of this it deals with inspection type of activities, maybe meeting some sort of requirement. And then the non-value added activities are things that really have no bearing whatsoever on the patient outcome or the patient customer service. So counting activities, inspecting activities, inspecting that is not required for some accreditation, for example. So inspections, transportation, moving, maybe stocking or storing activities, rework, so meaning we had a defect, so now we need to do a rework. Those are the types of things, so non-value added, meaning it's something that's not required and it's not providing any value to the customer. So in here, the middle one is really something that is required for some reason or another. You are required to do this, but the customer doesn't really see any true benefit. So here's an example, and we have in green the customer value added steps. In amber, kind of that orange tint, is non-value added but required. And then the red is purely a non-value added and not required. So you can look through some of these and see anything where we have that kind of that half oval where there's waiting time involved, that's certainly going to be a non-value added in a red activity. And you'll note that here. Sometimes the amber, maybe we need to secure approval, or there's some required form that needs to be done for some reason. So some of those are not value added for the customer. Customer doesn't care if you get approval or not. They're not seeing any gain, but it's something your organization requires. It's something maybe an accrediting body requires. And then the green are things that absolutely are valuable to the customer. Okay. Now, a value stream map often will include things like this, but then you could have some times. So we talked earlier about process times, we talked about cycle times. So if you have those times on your map, you can use those to identify where there might be a bottleneck or where there might be some process delays. And then how long the waits, the delays, the process steps take, so that you can try to enhance your process. But otherwise, this is a pretty good value stream map. You have the 6 different activity types, I guess you'd say. You have the client manager and what that person needs to do, the client HR and what that person needs to do, and so on and so forth. So here we have another value added time example. So if there are tasks, and here we have 3 tasks. So we have a prelim exam by a nurse, a physician exam, and then a patient check-in. So we think about this in terms of what is value added to the customer. And so we start by saying, okay, is the nurse prelim exam value added? Yes, it is, because the nurse is identifying or looking at the patient, examining them, and then identifying maybe some initial concerns. So then what would be next? Well, the physician exam. That's why the patient is there. Patient is getting examined by the physician to identify what is the illness, or what is, or getting the actual surgery or what have you. The reason they're there is to see a physician. And then we have, out of those top three, what could be a non-value added step, and that could be the patient check-in. The patient doesn't see any real value from checking in. It's essential for the organization, so it could be a non-value added required task, but it's not really adding any value to the patient. Okay, for the last part of this session, I just want to show a value stream mapping video.
Hi, this is Arthur, and let's talk about value stream mapping for Lean. I call it Lean Simplified. And let me introduce you to the power tools for this. They're called post notes. I use the square ones for activities and the arrows for the gaps between activities. And let me give you an example. I worked with a group a while back, and it was taking them 140 days to process a transaction, if you will. And that just seemed entirely too long. And so what we did was we started to lay out the value stream, the map of what happened. And first step, log the request. And then they'd evaluate the request. And then they'd research the request. And then they'd decide if the request was valid or not. Then they'd schedule an exam, diagnose the patient, and treat that patient. Now, at this time, this 140 days was the fastest of anywhere in the nation. Now, I always use these little arrows to show the time in between. But here's what I've learned from working in a lean environment with many different kinds of processes. You quickly discover that maybe 3 minutes out of every hour are spent with people doing something, or machines doing something, but the other 57 minutes are all spent the product's waiting on something to happen. I call this the 357 rule. So what happened here was I asked them, I said, okay, so how long does it take to log the request? And they said, maybe 5 minutes. I said, okay. And then how long does it take to evaluate the request? And they said, 25 days. I said, really? You got one guy, one sheet of paper, working on this for 25 days? And they said, well, no, actually, it's maybe 30, 40 minutes to evaluate the request. And I said, oh, so there's 25 days of delay. They said, yeah. I said, okay, so what happens next? Well, we research the request. Really? I said, how long does that take? And they said, 120 days. I said, really? 120 days? One guy, one sheet of paper? And they, well, no, that might take an hour. I said, so there's a 120-day delay. And very quickly you discover out of this 140-day process, a lot of it is stuck in these two boxes right here. Then, if it's okay, they schedule the exam. I said, how long does that take? Maybe 10 minutes. How long before you actually get to do the exam? Well, as much as 7 days. And then it might be, maximum of 1 day before you get around to treatment. The diagnosis, maybe an hour. The treatment, that could be ongoing. So what you discover here is, in that 140 plus days, there was only 7 hours of real work in the entire process. So once you've mapped the value stream, then you want to figure out, well, how can I redesign this to get rid of these big delays, especially that one and this one on top of it? I said, well, could you just log the request and get right into evaluating it? Well, maybe. I said, well, can you do the research request in the background? And the doctor said, well, we can usually tell from looking at the patient whether what they're asking for was really caused by what they say it was caused by. And so, literally, we could take it and go straight to schedule exam, eval, schedule, and get right into diagnosis. And they actually cut this process down to about a maximum of 30 days now. And that's how easy it is to redesign and reevaluate a process using value stream mapping. In the background here, I have a picture of a painting of Jimi Hendrix by a guy named Denny Dent. And if you go on YouTube, you can watch Denny paint this particular picture in about 3.5 minutes. It's 4 feet by 5 feet. And he gave me permission to be a little bit more loosey-goosey with the value stream mapping process. You can get into all kinds of detail telling what each one of these things does, but until you get rid of these giant delays, all those little things, irrelevant. Anyway, that's the essence of value stream mapping and speeding up your processes. Thanks.